Am I audible? Okay, good. All right, thanks for having me. Thanks for staying around. So I'll continue on the same theme as what most of the speakers have been speaking about, except that I'll try to make you fall in love with Lindblad all over again and try to show that most of the things that was said previously, which is mostly in the few body cases, may not apply about, in terms of Lindblad failing and all that. So we'll compare the Lindblad results with a host of other results, and we'll see that it agrees quantitatively, qualitatively, with a whole bunch of set of approaches: Kubo linear response, memory functions, TDMRG, qualitatively and quantitatively. All right. So the two works that I'll be mostly talking about is this and this. The motivations from both these came from a series of works that we and others did previously. It was inspired by anomalous transport properties that was seen in a couple of works here approximately 2 years ago. These are all published. I forgot to put the published version that's in PRL, PRX, JSTAT. The technique of the Lindblad driving in the many-body spin chain case is described in this very nice article by Tomasz Prozen and Marko Žnidarič. So in these cases, we were and they were looking at disordered chains at high temperature and transport of excitations, energy, spin, and so on. We continued that, and this was for reasonably small systems and so on. So we continued that in a much more rigorous and much bigger chain settings, and this was again a disordered and interacting chain. And then we realized, maybe we don't need interactions at all. We can just probably do away with interactions and change the type of disorder. And that resulted in these two papers. And indeed, you do find, so this was Kubo linear response, and this was Lindblad setting. And we do find that, as we saw from a previous talk yesterday, we do find that you do have anomalous transport again. And then again, we went on. So this is the first 20 minutes. Well, this is the next minus 20 minutes, and this is probably I won't get to that at all. And then we sort of realized that we probably don't even need disorder. We can just work in a purely interacting chain, and we can still get anomalous hydrodynamics. And so this is the paper which will hopefully come out soon. Okay, so firstly, just a bit on transport and disordered systems. So usually when we think of transport and disordered systems, there are two paradigms which we think of. From the Einsteinian sense, there's diffusive transport, right, Brownian motion, stochastic, and all that. But then 50 years later, Anderson comes along and says, if you add sufficient disorder, or in particular kinds of disorder, you can actually completely suppress diffusive transport even. So these are the two kind of broad themes which were around for a long time. But diffusion, it really rests upon a couple of assumptions. The first is the continuity equation is exact, right? So with diffusion, it really rests on the fact that you assume a fixed first law, right? So in which the current of the propagating excitation is proportional to the gradient, and the proportionality constant is the diffusion constant. That gives a phenomenological transport equation. And what we want to argue is that this transport equation can fail in certain circumstances. Now, this is not new. This is, you can have anomalous transport in a whole host of situations. You have this generalized fractional Laplacian, which I don't want to describe right now. You get these in stochastic dynamics, Levy flights, and so on. You get it at criticality. So this paper that I refer to is the 3D Anderson model, non-interacting. At criticality, you get anomalous transport again. And more recently, which is the first theme of the talk, in the many-body interacting case, you get what's called the Griffiths anomalous transport due to Griffiths fractality. So these are sort of rare region effects, right? Okay, so again, we've seen the Lindblad's master equation a couple of times. You have these two parts, unitary and dissipative part. I won't try to justify the use of the Lindblad master equation in a many-body context. Already we've seen in the single-body context there are problems and so on. Our approach is a very pragmatic approach. We take the system, we apply the Lindblad description to it and see how it works and see what it gives and compare it with other results. And we see that it agrees quite well. There's also a very nice sort of opinion piece by Steven Weinberg about, it's a sort of, if you want to call it an Einsteinian lamentation about how there are problems with quantum mechanics and so on. But he sort of suggests that maybe some of these problems can be alleviated by using a Lindblad equation. And he has a PRA from this year and last year as to how you can actually, using atomic clocks, maybe show that the Lindblad equation can be used to model quote-unquote reality. Anyway, that's a philosophical aside. So what do we do? So as it's specified right now, the LKs, these are the Lindblad operators. These are unspecified right now. The way we specify them is to impose on the boundaries that the two chains at the boundaries will thermalize to a given density matrix that we put in by fiat, right? And the density matrices that we put in are e to the minus mu times sigma z on one side, e to the minus mu right times sigma z on the right side, right? So, and imposing that as the thermal states of these two spins, and under completely non-unitary evolution, we can construct these LKs. And that's what it turns out to be. So you can see that for a non-zero mu, as long as mu is non-zero, you get a current flowing this way, and you get a current flowing this way, which will be unequal in magnitude if mu is non-zero. And you can trivially see that if mu equal to 0, the final steady state, if mu equal to 0, the final steady state will just be the identity operator. You can just put that in and it's trivial to check, which means that we are, if mu is small enough, which means we are working very close to equilibrium and we are working very close to infinite temperature. Right, so we evolved this with TDMRG up to very long times. It's not a problem with entanglement growth because it's not unitary time evolution. For the details, I can speak about it later with you, or I can refer you to that article by Tomasz and Marco, Prozen and Zinerovich. Right, so once we have the final steady state, we can measure observables in this, right? So any observable, so two primary observables that we'll be focusing on are the current, the steady state, final steady state current, and the particle density. So just again, a small aside, because we'll be referring to this a couple of times. The scaling of the current will determine the transport rate. So if it's 1 over L, as we saw yesterday, if it's 1 over L, it's diffusive as a function of system size. If it's even faster than that, it's subdiffusive. If it's slower than that, it's super diffusive. And if it's constant, it's ballistic. Now, you can do some dimensional analysis and relate the usual wave function spreading exponent with this current exponent. So that's the relation that you'll have to sort of remember. This is, I'll try to justify, well, okay, let me say that this is not the only possible relation, right? So this is, we've seen that it breaks down in some cases, we've seen that it works in other cases. So this is a purely dimensional analysis kind of relation. Yes? No, oh, no, gosh, no, way. No, this is, as long as you want, 100, 200. Yes, so these are the spins, sorry. So these are the spins, and these go, we go up to 100 sites. I just meant to, you're right, I should have put some dots here. There are interactions. So we consider two cases. The first case that we'll consider is with a disordered and interacting chain. The second case we'll consider as a quasi-disordered and non-interacting chain. And in both cases, we have reasonably quite large systems of the order of 100 to 10,000. Right. So this is the first model that we'll be looking at. That's the Heisenberg chain with interactions, and it's fully disordered, fully interacting. Everything is of order 1. Delta is of order 1. The hopping is of order 1. Interactions are of order 1. They are much stronger. I won't make this extremely large. I won't go to what's called the localized phase. I'll stay somewhere here. So I'll stay at most h equal to 2 and 2.5. Just to be clear, in this model, the localization transition happens at h equal to 3.5. But we'll stay up to h equal to 2, which means we are not too close to the localization transition and we're not too far away. There are problems going closer to the localization transition, which I'll explain if the question comes up, using the Lindblad setting. There are genuine problems. So there we cannot go all the way till here. So that's the setting that we are interested in. As Stefan mentioned yesterday, there's a localization transition from a thermal phase to a non-thermal phase as a function of disorder strength in this model. And so H governs the disorder strength in this setting. Yes. This was shown for a closed system. Right, so this is for a closed system, indeed. Yep. All right, so what do? We do the same thing that we saw yesterday for the quasi-disordered case as well. But this is the interacting and disordered case. We can go to pretty large system sizes and for a range of disorder strengths, right, H equal to 2. As I mentioned, H equal to 3.5 is where the localization happens, which means this curve should just go exponentially down. And we really cannot simulate it for many other reasons. Couple of observations. Let's start with the H equal to 0, the clean case. Already here you see that it's not diffusive, it's super diffusive, right? And super diffusive with 1 by L to the 0.5, which means if you convert it to beta, if you put 0.5 here, you get 2 over 3, right? You get beta equal to 2 over 3. So that's a super diffusive case. Now this already, it agrees quantitatively. This 2 over 3 agrees quantitatively with long-time unitary T-DMRG simulations, which was in this very nice paper, in this Nature Communications paper. It also agrees, again, quantitatively, this 2 over 3 exponent. It's not, well, the fact that it's super diffusive already is not trivial, according to me. Because it's an integrable chain, you would expect H equal to 0 is you retain integrability. You would expect usually some sort of ballistic contribution, but it's super diffusive. So it's for A, it's super diffusive. B, the super diffusive exponent is 2 over 3, and that agrees well with this paper. It also agrees well with some memory function analysis that one can do, and independent Kubo linear response that can be done. That's in this soon to be appearing paper. The Lindblad. I'm only using Lindblad in the whole thing. Yes, TDMRG, right. This is unitary time evolution of TDMRG. So what they do is they take an inhomogeneity, right? So they begin with the density matrix with a slight inhomogeneity in the particle density, and then they evolve it, and then they look at how the difference in the inhomogeneity disappears. That's a closed system, right? So I'm just trying to make the point that in the closed, there's agreement between I just put this in last minute since there was some Lindblad bashing. I just put this in just to show that there is agreement between closed and open, Lindblad, and other methods, right? No, this is all from the first paper. Oh, sorry. So this is all from the first paper. I just meant the numbers agree for this line. No. So in that setting, it's a different variable that they're measuring. So all of this is in the first paper that I mentioned. In our first paper that I mentioned, I should probably write it on each slide, but I tend not to do that. So it's in this first paper that I mentioned. Right. So in the disordered case, which is much more difficult to simulate using other methods, we just use we use the Lindblad, and what we find is as you increase disorder strength, the slopes start getting steeper, right? But there's a caveat. As you can see, if you had stopped here, for instance, in the weak disorder strength, you would have assumed that you would have thought that this is super diffusive again, right? The slope goes this way. But then as you increase the system size, it goes parallel to the 1 over L, which means it's diffusive, right? So you can see that there's a length scale L star below which the system sort of doesn't feel the disorder strength. And that's reasonable. That's reasonable for these small h values, because for these small h values, the mean free path is just so long. It almost feels like it's clean, right? Yes, which is why the super diffusive is already an interesting finding, I think. And so if you have this L critical length scale L star, you can try to understand that from Fermi-Golden rule, which is you begin with an excitation. I won't do the calculation here due to lack of time. You begin with an excitation. You assume that these quasi-particles are free, so it has a cosine dispersion. I mean, this is, cubical cow approximation, but it works very well with the scaling. You assume that the quasi-particles are free, and then you estimate the time at which it first disperses by the disorder potential. And you can estimate that this L star is 1 over h to the 2 beta. So you scale the x-axis by that. You scale the y-axis by a different it's not quite different. I don't want to explain this. And you see it all fits nicely in one curve for different h values. So this is all in the diffusive regime. So you can clearly see that at around x equal to 1, there's a change there's a crossover from the super diffusive, which is 1 by x to the 0.5, to the diffusive case, which is 1 by x. Right. So this was this means that as you increase the disorder strength, the system doesn't immediately become subdiffusive. It doesn't anomalously transport excitations. So, which means if you go back to this slide and you start extracting the gammas, the thermodynamic gammas, you get this curve. Now, this is the gamma as a function of h in this fully disordered, fully interacting, high temperature system. So you begin with a super diffusive case, you immediately go diffusive, you stay diffusive for a bit, and then you start becoming subdiffusive. So you have a fully subdiffusive regime in this model. Yeah, qualitatively. So the Agarwal paper, they had very small system sizes, and they were doing Kubo linear response. But qualitatively, yeah, they do find a diffusive regime. They get the super diffusive part incorrect. Well, no, let me take that back. They don't find it, but some other group which do similar things that the Agarwal group does, they find the diffusive, which is incorrect. So it's actually super diffusive. But they also do find there's a diffusive plateau. Not quite, no, not quite, no. Right, so you see, so this is the upshot that I want to put out, which is around this isotropic point, you have a whole regime of transport rates. I didn't show you results for the gapped phase or the gapless phase, but the gapless phase, you can rigorously prove that it's ballistic. In the gapped phase also, you cannot rigorously prove that it's diffusive, but this is, in my mind, this is still an open question. There are still problems with how diffusive it is. I'm talking about the clean case. Because you can find, you find that the second moment of the current scale as though it's diffusive, but higher moment scale as though it's non-diffusive. So anyway, I just left it as diffusive just to avoid confusion. So you see there's a whole zoo of things happening here. There's super diffusive, there's ballistic, there's subdiffusive, and so it's a very rich diagram, dynamical phase diagram. Then there's localization sitting around here. Which is also kind of suggests that maybe we should stay away from this kind of model. In terms, if you want to find transport rates, maybe it's best to begin with a non-integral model to really completely understand what the transport rates are. Yeah, I think since I'm out of time, there's actually a second part of the talk, but I could try 5 minutes. All right, fine, okay, fine. Thanks. So I won't speak about these two works. So we have similar and more effects, actually much more interesting effects for the energy, which I won't be talking about. There's a question mark on this soon because this calculation has been going on forever. Anyway, so the second part of the talk is, which I'll really rush through, because some of it we saw yesterday, is since we know anomalous transport has been seen in quasi-periodic systems, even for the Anderson systems at criticality, perhaps we should revisit this in this Lindblad setting. And these are a couple of papers which show that you do have these anomalous transport properties at criticality if your wave functions are critical. So in my mind, most of these properties which show anomalous transport has to do with multifractal wave functions. And this still has to be fleshed out. Okay, this I won't go through. So in 1D, as we saw yesterday, there's a phase transition between a localized and a delocalized phase. This was shown by Aubrey and Andre. Now it's a free model. Now I'm switching off interactions, switching on correlations among the disorder. Right. So and then the question that we want to ask is, if you have a critical point, how stable would these closed system anomalous properties be to driving? I'll skip over a bit some, I thought, very nice slides about fractality and so on. But that's the main question. How stable are these fractal properties driving at the transition? So just an aside, in the non-interacting case, in the Lindblad setting, you can get an exact non-equilibrium steady-state solution, which you cannot get. So in terms of, you can replace these by integrals, and you get, essentially, it's exact. Now, what are these eigenfunctions and eigenvalues? These are eigenfunctions and eigenvalues of a suitably defined non-Hermitian matrix. Again, I can explain what this suitably defined non-Hermitian matrix is after the talk. But the fact is, you can compute it exactly, and you can either do TDMRG to evolve it, or you can just do it exactly. So even in a many-body setting, even in a many-body Lindblad setting, you can get exact solution. You don't have to just do any GF, for instance. Right. So what we find is, at criticality, if we look at the steady-state magnetization, we get these very funny magnetization profiles. So that's X, that's the chain, that's the 0th side, that's the Lth side. I just scale it by L. And we find that depending on number theoretical properties of the chain, whether it's a Fibonacci number or it's a non-Fibonacci number, we get completely different magnetization profiles. Now, you see these little hairy little things, it's not noise. They don't go away by disorder averaging. As you can see, it just falls right on top of each other for two different Fibonacci numbers. And I haven't shown this here because if I put another non-Fibonacci number on top of this, it'll just be noisy. But if you take this non-Fibonacci number L divided by G, the golden ratio, and take the floor of that, take the closest integer, although this looks like noise, it just falls bang on top of it. I can show you, that's in the supplement as well. So you see, the error bars are smaller than the symbol size. So this is not noise. So we suspected, well, it was much more clear to suspect that this is probably a fractal feature emerging in a non-equilibrium steady state. It's not so clear here. I mean, here it just looks like noise, which just didn't go away upon averaging. But in fact, if you do the box counting technique that's one of the ways of estimating a fractal dimension of an object, which is if you have an object and you fill it with boxes and you keep decreasing the size of the box, and then you ask, how many more boxes do you need, right? So it grows as a power. So if that power grows linearly, that's a one-dimensional object, right? So if the number of boxes required to cover a space increases linearly with the size of the box, it's a 1D object. If it increases as a squared, it's a 2D object. But if it's in between, it's a fractal object. And so that's what we do for these magnetization profiles. And we find in the Fibonacci cases, you have reasonably small fractal dimension because it's close to 1. One would be boring. For the non-Fibonacci case, you find higher fractal dimension. So that's one takeaway message, which is that you have these non-equilibrium fractal signatures coming up in the steady state, which we thought was an okay result. So this is, again, now we go back to the transport. That's a second quantity we can measure, which is the two-particle function, right? And again, we see there are differences between Fibonacci and non-Fibonacci. Again, I won't have time to justify that this is not noise. This actually collapses nicely onto, if you take a set of numbers, this also collapses nicely onto a curve. And there's a nice scaling where everything collapses close to L minus P, L minus F. So for this, we had to define, to justify a scaling for these, we have to define a secondary set of Fibonacci numbers. But again, I won't go into that. Anyway, the upshot of all that is, at criticality, so that's the upshot. At criticality, you have fractal dimensions in the profiles, and you have subdiffusive dynamics. Right now, again, I'll just flash this very quickly. So we do the closed system wave packet spreading, and again, as we saw yesterday, there's some discrepancy between open system and closed system, which we think we can explain based on the slide that I showed for the exact solution, but that's still work in progress. You do observe weak subdiffusion in the Fibonacci lattice if you choose your potential to be symmetric. Now, I really want to, I want you to focus on this line. This is a line on top of another line. There's no disorder averaging here. It's just one sample and one fit, and it's really just on top of each other. So you see, that's quite convincing, I think. So, right, the upshot of this is that there is a discrepancy between open and closed system dynamics. And that, again, I think should be understood from the fractal structure inside the Aubryon ray. All right, so the conclusions are we see anomalous transport in these Lindblad-driven systems which are interacting and disordered, or non-interacting and quasi-disordered. And we've sort of, I don't want to say, well, we sort of, we see these non-equilibrium fractality signatures. Yes, that's about it. Thank you.
So are there any questions?
So, I mean, why would you do this non-interacting case by using that method? I mean, that's easier to do with the, you can do it exactly. I mean, why would you do it?
Exactly as in?
Using NEJF, it's exact. I mean,
sure. No, even I would argue that even these set of formulas that we wrote are exact. I mean, there's no approximation. This is solved exactly.
But starting from your Lindblad description.
Starting from the Lindblad description. Correct.
Yeah, but I mean that, and also your this Lindblad expression is the temperature is always infinite, is it?
Yes. Yes.
So there is no way to go to lower temperatures or something like that.
There is, but there is a problem in trying to detect. If you have a mobility edge, there is a problem in trying to detect mobility edges using the Lindblad setting and trying to tune the temperatures, which I think cannot be done, but I'm not sure. But we are still thinking about that.
And just one more question is that beta, you showed some beta equal to 1 by 1 plus gamma, or
yes.
Can you sort of justify that expression somehow?
Sure. Okay. So fine. So let's try that. So you see, if you have particle spreading x squared going to t to the 2 beta, right? You can imagine L goes as, how's that? L is t to the beta, right? Which means t is roughly speaking L to the minus L to the 1 by beta, right? So this is for particle spreading. This is closed system dynamics, right? Now, if you assume that the current in a system is simply, just by the Drude model, is proportional to velocity, NE squared V, right? So V is simply L over T, and T you put this as L by L to the 1 by beta. Now comes the big sort of leap of faith, which is, this is all closed system. Now we go to the open system, and this is L to the minus gamma. We just relate the gammas and the betas. Right, so we see that this agrees, this fails miserably in the generic Aubryon ray. It agrees for the symmetric case. Yeah, that's one point I wanted to mention, actually. So this curve that we have, this slope that we have, it agrees quite it fulfills this relation quite spectacularly if we look at the closed system dynamics. So it would be nice, I mean, so I know you have this work, it would be nice to do the similar thing for the perfectly symmetric case and see if the exponents agree as well.
You had mentioned in the interacting model that there is an issue as you approach the MBL transition.
Yes.
Say more about that.
Okay, I can. The problem is you have, in the Liouvillean that you have, in the, well, I don't want to go all the way, but you know the Liouvillean that I mean, right? So in the Liouvillean, you have a Liouvillean gap, and that closes very, very quickly as you go towards the MBL transition, which means you have to simulate for much longer times. And that's the only problem. So if you have time, you know, you can simulate it. If you don't have time, then you can't.
So you don't have a gap, or you do have a gap in the Liouvillean on the delocalized?
You do.
You do?
Yeah, yeah, it starts getting smaller and smaller.
Okay.
Yeah.
No. So you have. I'm just a little concerned about. So you have this. You had this spin chain, right? And that by Jordan-Wigner maps to free fermions.
Mm-hmm.
And your Lindblad also was a function of this local spin operators. But then in the fermion picture, it seems to be some Jordan-Wigner strings, right? So it seems to be an extremely strange bath in the fermionic language.
Right. So,
I mean, maybe this is some confusion I have to resolve myself, but do you have anything to say about it?
well, the thing is, the way we choose the baths at the end, the actual Lindblad operator, as I mentioned, there's some arbitrariness of how you choose the actual Lindblad LK operators, right? So these operators, how do we choose them, right? So we choose them, and we chose them by imposing a particular kind of density matrix at the end. So you don't have to necessarily do the Jordan-Wigner for that, right? Correct.